exercises, etc. So we will keep that for the next session, and today's lecture we will take an introduction into the next chapter, which is kinematics, okay, which is also basically there is quite a bit of application of calculus in kinematics, okay. So kinematics is basically the physics of motion. So what we do here is we study equations to define the motion of a body or a particle or whatever. Okay. And without describing the cause of motion. And the cause of motion is basically forces, which is part of what you're studying in Newton's laws of motion. Whereas here, we don't get into the cause of motion, so we don't talk about the forces acting on a body, but only we talk about the equations of motion itself. So let's start by understanding the parameters, okay, which are basically the physical quantities that we use for describing the motion of a body. Okay. Now, before we get into the physical quantities and all this, one thing further we'll understand that in this section of kinematics, we are basically studying what is called particle kinematics. So which means that even if we are describing the motion of a rigid body or a large object like a vehicle or something, we will treat it like a particle. Because its motion does not involve rotation. Okay. Rotational kinematics of rigid bodies, for example, the spinning of a fan blade or rotation of a cylinder rolling down a slope, etc. These kind of things will be studied in a later chapter. So that's just something we should understand before we get into the parameters. Okay, so in this chapter, we will not be dealing with those kind of situations where a rigid body is in rotation. So a simple example is like if I were to throw a rigid body like this pen in the air, so it might be going like this. So while it is moving, what's happening is that it's also spinning. You can see that the pen is about its center of mass. It would be rotating like this. And while it's rotating about its center of mass, it's moving through the air like this. So that is a more complicated type of motion, which involves the combination of two things: rotation, that is a spin of the pen happening about its center of mass, okay, along with what we call projectile motion. That So we are not studying like that, something like that. We are studying something more simple, like if you throw a ball without giving it any spin in the air, so it just simply goes like this, okay. Like this object, it might be just going like this without spinning happening about its axis. So that type of motion is the one involving no rotation. So that is where we can treat the rigid body like a particle. Okay. And that is what we are going to do over here, which is called particle kinematics. Whereas something which involves rotation of a body while it is in motion, that will be studied under a different section called rotational kinematics, which will come in a different chapter a little bit later. Okay. So just this point we need to understand over here.
So, sir, we are considering about vacuum medium.
No, we are considering any medium. The object can be moving underwater, it can be moving through atmospheric air, it can be moving through the vacuum of space, whatever. It can be moving under the influence of gravity, or it might not be moving under the influence of gravity because it's moving on a smooth surface which is supporting its weight. Everything considered. Understood the point, no?
Yes, sir.
It can be sliding down an inclined plane. So okay, so hope this point is clear to all of you. Okay. So just finally one more thing. So when the motion is of this type, that there is no spin involved or there's no rotation involved, it is given a technical name and it is called pure translation. Okay. So additionally, when a rigid body is in motion such that it is not rotating, okay, its motion is called pure translation. In such a case, only it can be treated like an equivalent particle to describe its kinematics. Okay. So now, having understood this, let's come to the physical parameters which describe kinematics. Okay. So the first thing we describe over here is position. So position is described as a vector now. So another way of defining it is position vector, which we denote with the symbol R. So this is a vector joining the origin of the coordinate frame. So you also call the coordinate frame as the reference frame. Because the motion is studied in reference to that frame. So basically, if this is our system of coordinate axes, normal three-dimensional XYZ system in general, and this is our origin. Now, if our particular particle is located at this point right now, let's say its coordinates are x, y, z, okay, then its position vector or its position will be described by a vector, which is this one, the one joining the origin with the location of that particle. And that vector is denoted with the symbol R. And as you can see, its position vector R will be x I cap plus y j cap plus z k cap in general, where x, y, z are the coordinates of the particle P with respect to the reference frame. So now one simple thing we can understand, that if a particle is in motion, okay, then its position R must be changing. It must be varying with time. So that becomes like a definition of rest or definition of motion. What is a particle at rest? One whose position vector is constant, it's not changing. What is a moving particle? One whose position vector is varying with respect to time, changing with time. It could be that one of the coordinates is changing, it could be all three coordinates is changing. But if the position vector is changing with time, then by definition, it is in motion. If it is not changing with time, that is the position vector is constant, that means we will describe that particle to be at rest.
So what is the exact definition of reference frame?
Reference frame is basically a coordinate frame that is used for referencing of the motion. Like, so the motion will be defined or measured with respect to that particular coordinate frame. You understood my point? No?
Yes, sir.
So according to the convenience for the person who is, writing the equations, he or she will select some particular point as origin, some particular direction as his x-axis, then y-axis can be any axis perpendicular to the x-axis. And moment your x and y-axis are selected, then z-axis has to be selected according to the right-handed system. You know that right-handed palm rule or right-handed thumb rule. You know about that, right?
Yes, sir.
From vectors, so that your I cap cross j cap will be the correct direction of k cap. Right? So that is your reference frame. Just a moment. Okay, so the concept of reference frame is clear. Right? It's basically just a coordinate frame that is selected by the person or whoever is writing the kinematics equations according to convenience. But yes, the coordinate frame has to be what is called a right-handed rectangular frame. That means the x, y, z axis have to be mutually perpendicular, and not only that, they have to be according to the right-handed system. That is, I cap cross j cap is equal to k cap according to the right-hand palm rule. Okay. Now, having understood position, next thing we come to that, assuming the particle is in motion, the position is going to be changing. So the first important parameter about the changing position or about the motion is something called the displacement, as you know. There's also, of course, distance, and that's a little bit more complicated. We'll come to that later. But let's start with the displacement. So typically we denote the displacement as the vector S, and it is described as the vector joining the initial to the final position of the particle. Okay, so you have earlier studied the definition of displacement probably as the straight line or the shortest path from initial to final position. So that was like a common definition of displacement. Now we come to the vector definition of displacement. Now that you've studied vectors and you understand the language of vector algebra, so we can describe it as the vector, the shortest path or straight line. It just becomes a vector which also points in a particular direction. Okay, so that's why. So let us say that this was the position of the particle at a certain time t1. So I will write it as position vector r1. So this is where our particle was, x1, y1, z1 at some time t equal to t1. And now after some time, the particle has reached here at time t2. So t2 is greater than t1. Okay. So now the particle might have taken a very complicated path. It might have gone by some path like this. Okay. But that's not important as far as displacement is concerned. The displacement is just going to be the vector that joins the initial position with the final position. So now this is my position at time t2, this vector r2. which joins this point x2, y2, z2 with the origin. Okay, so now my displacement vector during this time interval from t1 to t2, as the particle has moved through whatever path but changed its position from this point to this point. So the displacement is going to be the vector joining the initial point with the final point. So this is the displacement. So in this example, we can say this is the displacement. So here S is the displacement from t equal to t1 to t equal to t2. Okay, as the particle moved from the original position r1 vector to the final position r2 vector. Okay, so now what you can see in this diagram over here is very interesting, that this vector S is nothing but the difference of these two vectors, r2 minus r1, because you joined r2 and r1 from a common origin, right? And then you are joining the vector which is from the head of r1 to the head of r2. So it is nothing but the difference of these two vectors. So now the mathematical definition of displacement is that it is the final position vector minus the initial position vector. Okay. Or even simpler, we can say S is delta R. It is a change in position vector. So we can say in words that the displacement is the change in the position. Of course, thinking of it as a vector quantity. Okay, so with the help of vectors, our definition of displacement becomes something even simpler. It is just the difference of the final position vector minus the initial position vector. Okay. Of course, as you probably already understand, that the dimension of the quantity displacement is length, and its unit is expressed in meters in the standard international system, or centimeters in the CGS system. Okay. Or sometimes we use longer units like kilometers, miles. Same for position, of course. Position also is expressed in meters, kilometers, etc.
Yeah.
Yes.
So shouldn't R2 be the displacement of the entire path from t is equals to 0 to t is equals to t2?
R2.
Yes, sir.
No, beta. See, R2 is the final position, na? So R2 is basically the line joining the origin with the position x2, y2, z2. Got it, na? But did the particle start from the origin? No, na? It started from R1. You understanding my point, na?
Yes, sir.
Had it started from my origin, then my
No, sir,
R1
it
would be
didn't.
zero. In that case, R2 would have been the displacement. But here I'm assuming that at time t1, it started from not the origin, somewhere else. It started from that point x1, y1, z1. And by the time I'm coming to time t2, it's reached this other point, which is x2, y2, z2. So in that case, you can see now what the displacement is. It's clear now?
Sir, how the position of an particle becomes a vector?
Yeah, so that's how we describe it as a vector. Na? It is a vector joining the origin of your coordinate system with the position of the particle, with the point where the particle is located.
Okay, हाँ, okay, sir.
Got the point, ना? So अगर उसके coordinates x, y, z है, तो position vector क्या हो गया? It is x I cap plus y j cap plus z k cap. है ना? Understood, ना?
Yes, sir.
Okay.
The
Yes.
direction of displacement can't be opposite.
No, beta. Displacement vector will always be defined as pointing from initial to final position, not from final to initial. Got it, no?
Yes.
So in addition to your earlier understanding of displacement, that it is a straight line joining initial to final, but now it is not just a straight line, it is a vector. So vector, straight line has a magnitude but no direction. Vector has both magnitude and direction. So displacement vector has to have the proper direction, which is pointing from the initial position to the final position. So hope this is clear, people.
Yes, sir.
Yes, sir.
Okay. So for example, suppose we have a situation like this. A particle is moving in a two-dimensional plane. Which is our XY plane. Okay. Such that its coordinates at time t are given by x is equal to 2 plus 3t and y is equal to 1 plus 2t square, where x and y are in meters and t is in seconds. So first of all, express its position vector r as a function of time. So when we do this, it is called the instantaneous position vector. Then secondly, find the position r at t equal to 0 and again at t equal to 5 seconds. Okay. And then we'll go on to find the displacement between 0 and 5 seconds. And we'll also find the magnitude of the displacement. Okay. So from now on, when we talk about finding the displacement or position or something, it's always going to be a vector quantity. So we'll have to use the unit vector notation, the I cap j cap notation for finding that value. Only when we say find the magnitude of displacement or magnitude of velocity or anything like that, then only we will come back to the scalar notation in terms of mod. Okay. So just work this question out quickly. Okay. What happened? Still nobody has sent the answer. So anyway, so let's look at it first thing. So the position vector at any instant of time is nothing but its x coordinate plus its y coordinate, j cap. There is no z coordinate because it's moving in the xy plane. So now we just have to substitute this in this to get it as a function of time as per the information of the question. So at any time t, the x coordinate is 2 plus 3t. That's it. And the y coordinate is 1 plus 2t square j cap. So in language of kinematics, we say this is the instantaneous position because it's giving the position as a function of time. So at any instant t, the position is given by this. Okay. So hope this is clear, people. Okay. Now, once you got this, the rest is just about following the instruction of the question. The second thing, we have to find the position at t equal to 0. Okay. So just substitute t equal to 0. So that is where the particle is starting its motion from 2I cap plus j cap, you can see. Okay, so if you just visualize this in the xy plane, so the particle would be starting its motion from somewhere here. Let's say this is where it is at t equal to 0. Its coordinates would be 2, 1. Now, for example, by the time we reach, what is it now, t equal to 5 seconds, its position would have become 2 plus 15. So that's 17 I cap. Okay. Plus 1 plus 2 into 25. So 51 j cap. So it's probably reached somewhere here. Its coordinates are 17, 51 at t equal to 5 seconds. Okay. And we want to just understand the pattern of the motion somewhere in between also. So you can see what is the position at t equal to 1 second. It is 5 I cap plus 3 j cap. Then t equal to 2 seconds. It would be 6 plus 2, 8 I cap. Okay. Plus 8 plus 1, 9 j cap. Right. So you'll realize that if you start plotting these different points, you'll see that it's definitely not moving along a straight line. It's moving along a curved kind of path. Okay, but we have to find now the displacement next. So the displacement is going to be just the straight line that is joining the position at t equal to 0 with the position at 5. So in the diagram, this is our displacement vector. This is our displacement from 0 to 5 seconds. So that's where the third part will come in. The displacement from t equal to 0 to t equal to 5 seconds. So what is our definition of displacement? It is delta r, change in position. So it is going to be the value of r at 5 seconds minus the value of r at 0. So that is 17 I cap plus 51 j cap, okay, minus of 2 I cap plus j cap. So the displacement vector for this interval of time from 0 to 5 seconds is going to be 15 I cap plus 50 j cap. So this is the displacement from t equal to 0 to 5 seconds. Specifically, if I take some other interval of time, the displacement will change.
When the instantaneous position is asked, won't we find the derivative? Like,
You can find the derivative. In fact, we'll see that what does the derivative going to give us? It's going to give us the velocity, because that will be the rate of change of displacement with respect to time.
oh,
So that's the next definition we are coming to.
So
And
it means that since we are expressing the position, we are not taking the derivative, but directly the term which is given.
come again, instead of the position, what is given?
So no, instead of velocity, position is given, and hence we are not finding the derivative of x is equal to 2 plus 3t or y is equal to 1
Here,
plus 2t square.
yeah, we are not finding correct the derivative here, because here we are asked to find the displacement and not the velocity, right? But if we were asked to find the velocity, then we would find the derivative. That's correct.
Okay.
Okay, so let's now work out the final part. The magnitude of the displacement, as you know, is simple vector algebra. So this is what you have to calculate. So here, for example, I can take the 5 common outside. So this is 3 square plus 10 square. So it is 5 into square root of 109 in meters. So square root of 109, I can do a estimated calculation like this, that I can write it as 100 plus 9 to the power half. Then take 10 common from it outside. So 1 plus 0.09 to the power half. Okay. And then I can use what is called the binomial approximation. So I can bring this power inside. So that is sort of approximate way of calculating something like this. So this will become and if you use a calculator, I believe that will be quite an approximate, that will be quite an accurate
Yes, sir.
approximation. You know? This is the magnitude of the displacement, which will come in meters. Okay. Whereas when we were expressing the displacement as a vector quantity now, or even the position as a vector quantity, again the unit was meters. But what it means is that each of the components is having the unit of meters. So basically what this means is that r at t equal to 1 is 5 meters I cap plus 3 meters j cap. Okay. Remember that the unit vector will never have a physical unit. I cap and j cap don't have the units because they are the same unit vectors that will be used for any other vector like velocity or acceleration or force, etc. So it cannot have a specific unit. But the component that we attach with it, the x component, the y component, etc., that's the quantity which has the physical unit. Okay. And that physical unit is the unit with which we are describing that particular physical quantity. So we are talking about a position vector. Each of its components will have the unit of length, whether that is meters, kilometers, whatever. If we are describing a velocity vector, then each of its components will have the unit of speed or meters per second or kilometers per hour or whatever. Right? So here also in the displacement vector, this is 15 meters I cap plus 50 meters j cap. So our magnitude of displacement is in meters. Okay, so hope this aspect was clear to all of you. Now we come to the next definition, which is velocity. Okay. So velocity is basically rate of covering displacement with respect to time. So that also becomes a vector quantity now. So velocity is a vector. So simply velocity is the rate of change of displacement with respect to time. So now, just like we had done in early part of calculus, we'll see here that there are two types of rate of change. One is the instantaneous rate of change. So that will be called the instantaneous velocity. Or we simply just call this the velocity. So from this point onwards, if we use the term velocity without any word before it, then it means that the default meaning of velocity is instantaneous velocity. So instantaneous velocity V is the instantaneous rate of change. Of displacement S with respect to time. So it's a simple definition like this. Now, before you write this down, one important thing here is that in a time interval dt, okay, the displacement ds is nothing but dr, because in general s is equal to what? It is delta r. So in a small interval of time dt, it is dr. So that's why what we write as ds by dt is the same thing as dr by dt. So instantaneous velocity is also instantaneous rate of change of position with respect to time. So these equations are both one and the same thing because of this condition, because we are talking about a differential interval of time or a very small interval of time. Okay. So that is our instantaneous velocity. Then the dimension of this will be length per unit time. So velocity is expressed in meters per second for the SI system, or centimeters per second for the CGS system, or kilometers per hour or miles per hour in other systems. You'll also remember this conversion. 1 kilometer per hour is equal to 5 by 18 meters per second, or reverse of that. So this is a useful conversion while doing questions and problems. Now, like we have described instantaneous velocity as the instantaneous rate of change of displacement with time, we'll also describe something called average velocity, which will be the average rate of change. So that will be total displacement divided by the time interval. Okay. We'll come to that, but when we just use the term velocity, the default meaning of the term velocity is that we're talking about instantaneous velocity and not average velocity.
But how we will differentiate a vector?
Good question. So I'm coming to that bit. So when we differentiate the vector, the unit vectors are constants. So the we just apply like the distributive property of differentiation. So differentiating a whole vector, so it is something into I cap plus something into j cap. So the differential operator then applies on the components. The unit vectors are just constants which remain outside.
Sir, what is that velocity is equal to Lt raised to minus 1?
Sorry, velocity is equal to?
Lt raised to minus 1.
That is dimension beta. Did you people have the board lecture on units and dimensions yet?
Yes, sir.
So in that, you would have seen that there's something called a system of dimensions, just like there's a system of units. So there are fundamental dimensions of mass, length, time, and 4 others. Okay, so they are denoted with a symbol capital L and capital T for length and time. So we say that the dimension of the quantity velocity, it's a derived dimension because it depends on the dimensions of 2 of the fundamental quantities, that is length and time. So it is length into time to the power minus 1. Okay. So if you haven't yet studied that dimensions properly, don't worry about it. It's a very simple chapter. Okay.
Sir, here the S vector will be a function of time, na?
Yes. It will be like the instantaneous position. So generally, we'll use this definition, dr by dt, because r is a function of time. Okay.
S is also a function of time.
So here in this definition, whether we are describing the velocity vector as ds by dt or as dr by dt, here s or r must be expressed as instantaneous values. That is, as functions of time. Okay. So for example, in that previous question, we had seen that if the position vector was that thing, 2 plus 3t I cap plus, I think 1 plus t square or whatever, or 1 plus 2t square it was. Anyway, it doesn't matter. But suppose I'm sticking to the same question. So 1 plus 2t square j cap. Now here, what will be the instantaneous velocity? If the position vector is this, okay, then the instantaneous velocity will be what? So velocity will be, one way is that I can just describe it as instantaneous rate of change of r. So now I need to substitute r as this one, because this is the instantaneous position as a function of time. I just need to put that value in. Okay. And then when I operate the differentiation, just treat I cap and j cap like any constants, like we do in differentiation. Okay. Because they are constants, independent of the motion. I cap is always the same thing. It is a unit vector along the positive x-axis. J cap is always the same thing. It's invariant. So it's not changing with time. So the differentiation now operates on the x component, and the whole thing gets multiplied with the fixed unit vector I cap, and then it operates on the y component, okay, and the whole thing gets multiplied with the unit vector j cap. So now you can just apply the normal principles of differentiation. So this is becoming my instantaneous velocity. And because this was in meters, now this is my instantaneous velocity. In meters per second. Okay. So this is the simplest way, that if I know position as a function of time, I can just find the velocity as instantaneous rate of change of position. I will show you the displacement method also, but that is unnecessarily a second step will be required for that. So better way to solve a problem like this, where r is given as a function of time, is to directly differentiate that r with respect to time, dr by dt. And hope it is clear to all of you now that how we can differentiate a vector quantity when it is expressed in component form. Yeah.
But here the r is the position and not the displacement, like delta. It is not the delta. Then how we can take that the velocity?
No, so see, that is the thing. See, we are describing the instantaneous velocity as a displacement in a very small time divided by that time. Now, during that small time, what is the displacement? It is the same thing as the change in position. No? You understanding? So that's why my velocity is becoming this ds by dt is equivalent to dr by dt, because what is the ds in that small time dt? It is nothing but dr.
Okay.
Okay. So I'll show this with a practical example calculation also using this same question. Okay. But conceptually, how we can understand, because this is what is the case, that during the small time dt, that small displacement ds that happens is nothing but the change in position, which is again that differential quantity dr. So, like if you try to imagine it, like let's say a particle is this particle only, it was moving in a two-dimensional plane like this. No? So during a small times, suppose it was here at some time t, and at a very small time dt later, it reached here. So this is the displacement ds. No? So that displacement ds is the same thing as the change in position dr. Okay.
Sir, it means that when we have to calculate the average velocity, then we have to differentiate R2 minus R1.
Then we have to take delta r by delta t, where delta
Okay,
r
sir.
becomes a displacement. So in average, it's a different thing, but in instantaneous, it's ds by dt is the same thing as dr by dt. Okay, so hope this calculation is clear to all of you, this example. So alternately, what I can also do here, we can first find the instantaneous displacement. From the given value of r. So instantaneous displacement s will be basically what? Displacement s from 0 to time t. Okay. So position at t equal to 0 is how much? From above you can just substitute. So it is 2 I cap plus j cap, and position at a general time t is how much? It is 2 plus 3t I cap plus 1 plus 2t square j cap. Okay. So now my displacement, okay, which is basically from 0 to t, this is the instantaneous displacement. That will be position at time t minus the initial position where it started from. So you have to just subtract these two vectors. Okay. So you will get 3t as the x component and 2t square as the y component. So now this is my instantaneous displacement. This quantity is the instantaneous displacement. So it is displacement as a function of time. So now if I want to describe velocity in terms of displacement rate of change, so I have to differentiate this, and immediately you'll understand why it's the same thing as dr by dt. Take the differentiation operator inside. So you can see the x component of velocity will become a constant because the x component of displacement was linear, whereas the y component of velocity will become linear with time because the y component of displacement was quadratic. So this is my velocity. So now, for example, if I ask, so this is again instantaneous velocity. Okay. So if I ask what is the velocity at a particular instant of time, like at t equal to 0, then you can see the velocity is 3 I cap in meters per second. At time t equal to 1 second, it is 3 I cap plus 4 j cap in meters per second. So it has a magnitude of 5. So what you can understand that in this particular case, if you look at the velocity vector, the x component is a constant, whereas the y component is linear with time, or it is changing with time proportionately. So that means along the x component, there is no acceleration, whereas along the y axis, there is some acceleration. Further, if you imagine, you will realize that this particle is moving in such a way that there must be some force acting along the y axis on it. So that force is giving it a uniform acceleration along the y axis, whereas there is no force acting along the x axis. There's no component of force along I cap. So that's why the velocity has a fixed x component. Okay, people. So hope this is clear. Now we
Yes.
come to this. Yeah. Good. Now we come to the second type of definition of velocity, which is always given specifically. We don't use the term just velocity for this. We have to specifically use the term average velocity. And that's why we have a specific symbol for it, V average. Okay. If we just use the symbol V vector, it means we are talking about the instantaneous velocity. So the average velocity is very simple. It is the average rate of displacement with respect to time. Okay. So in a certain interval of time, this will be the total displacement divided by the total time. Or we can now understand that the displacement is change in position. So it's delta R by delta T. So here S is the displacement during a certain time interval. Delta T. So we can also describe it in this way, that the average velocity is the change in position, let's say R2 minus R1, for a particular time interval T2 minus T1. Also write it like this. For delta T from T equal to T1 to T equal to T2. Here R2 is position at T equal to T2. So obviously T2 has to be greater than T1. We never talk about average velocity or displacement in a negative time interval. We always talk about a positive time interval.
Sir, if we differentiate it further, we'll get the acceleration, right?
Yes, if we differentiate the instantaneous velocity, that is, we have to express velocity as a function of time, like we've done in the previous example now, and then we can differentiate that once more, so we'll get the acceleration. So the third and final vector parameter, there is of course also speed and distance, which are scalar parameters, so we'll come back to those later. But as far as the vector parameters of this thing, kinematics is concerned, so position vector, displacement vector, velocity vector, both average velocity and instantaneous velocity, and finally acceleration. And since acceleration is also a rate of change, so there'll be two types of accelerations, instantaneous and average. So acceleration is rate of change of velocity with respect to time. So just write that down. I'll just be back in a second. Rate of change of velocity.
Sir,
Yeah,
sir, instantaneous velocity has to be a function of time, right?
exactly.
Sir,
Unless we
so
say what is the value of instantaneous velocity at t equal to 1 second or t equal to 2 seconds. If we just say instantaneous velocity, it means it's a function of time. Understood, no?
Yes, sir. Sir, but if the displacement or the position is a linear function of time, then differentiating would give us a constant.
Yes. So it's like that, no? Like we can have a constant function, like y is equal to 3 is a constant function, no? So its rate of change is 0.
Okay, sir.
But that's a special case, no? Okay.
Yes, sir.
So instantaneous acceleration is instantaneous rate of change, whereas average acceleration. So again, simply the term acceleration alone, it implies instantaneous acceleration. So the default meaning of the term acceleration is instantaneous, whereas the special case is when we are taking average acceleration. So for that we have the separate symbol A average. So that is delta V by delta T, or V2 minus V1 upon T2 minus T1. But generally what happens is that we talk about average acceleration very rarely. Average velocity is still something which is a useful term in kinematics. So we will be looking at it fairly often. But average acceleration is like, you can just say that, okay, we should know the definition, but it's hardly ever really used. Okay, so what we'll do next is, very quickly, we will take a special case of all these definitions. Of course, we have to also understand distance and speed, which are scalar quantities associated with kinematics. So we'll come back to that later. Now what we'll see is that how to change these definitions somewhat, or how to modify them in the special case of motion along a straight line. So what is called one-dimensional kinematics. Or in simple terms, motion along a straight line. So what happens is, if our motion is happening along a fixed line, then we can simplify all these parameters because there is only one component. So we need not use a vector notation at all. Okay. So the first thing we do is the line of motion is chosen as an axis of our system, like x-axis or y-axis or whatever. So our reference frame effectively just becomes an axis. It's not a coordinate frame anymore because the motion is just happening along one axis or one line. So you take that line as one of your standard axes, whichever one you want, x, y, z. Okay. So typically, if it's motion in a horizontal plane along a straight line, you can take it as the x-axis. If it's a vertical motion, like motion under gravity, you can take it as the y-axis. But there's no hard and fast rule like that. There's no reason why you cannot take a vertical axis as your x-axis or your z-axis. It's the choice of the person writing the equations. So our reference frame becomes an axis instead of a coordinate frame. Okay. So
So
position
what is
vector,
written, the line of motion is?
the line of motion is chosen as the axis. Sorry, this should be chosen. It's chosen as an axis of our coordinate system, x-axis or y-axis. So this is clear now. So position will just be given by a coordinate now instead of a vector. Okay. So for example, if the motion is along x-axis, then the position is just described by the x coordinate. So x as a function of time is the instantaneous position. So instead of describing the position by a vector xi cap, we'll just describe the position by the coordinate x. Because there is no y and z component at all. The motion is happening only along the x-axis. So accordingly, the displacement will be given by just a parameter like this. The velocity, instantaneous velocity will just become ds by dt, which is equal to dx by dt. The average velocity will be total displacement upon time, or delta x by delta. So instead of defining displacement as delta r, which will become delta x I cap, we just define it as this. Instead of defining velocity as the rate of change of displacement like this, here velocity just becomes and similarly acceleration so this can now also be described as d2x by dt square. So it's rate of change of instantaneous velocity with respect to time, or second derivative of position with respect to time. Okay, so first we will learn to solve various different types of one-dimensional motions, which is all going to be basically about the application of calculus, differentiation and integration in this context that the motion is happening along a straight line. And then we will come back to motion in a plane or motion in 3 dimensions. So that is motion in XY plane or all 3-dimensional motion in XYZ system, where in addition to calculus, we will also see the application of vectors. So what we have studied just before this, you can say they are the general definition of displacement, velocity, acceleration, and position for all situations. But when we specifically look at one-dimensional motion or motion along a straight line, then those general definitions become reduced to these scalar notation. Okay, we can still use a vector notation like I've done on the left-hand side, but all the vectors will have a common unit vector I cap. So there's no point in writing that unit vector separately. So we just, remove that because it's repeated for all the definitions. R is x I cap, S is delta x I cap, V is dx by dt I cap, acceleration is dv by dt I cap. So that I cap is common to all the vectors. So we need not specify it anymore. So we can instead use a scalar notation for describing these parameters. So you can just say it's a simplification of the general definition. Okay. But one thing should be clear to you that each of these quantities still has a direction, and the direction is given by the algebraic sign. If it is positive, then it is along the positive axis. If it is negative, it is along the negative direction. So one thing we should understand here that x is a coordinate, displacement, velocity, acceleration, all are expressed with algebraic sign, positive or negative. So the direction is described by this. So for example, if our instantaneous velocity is a positive quantity, but our acceleration is a negative quantity, we immediately understand that it's a case of deceleration. And the object's velocity will be decreasing because the acceleration is opposite to the velocity. But if the acceleration and velocity are both negative, okay, then it will not be called a deceleration, though it has a negative acceleration. It will be called an acceleration only because the magnitude of v will be increasing. Both v and a are pointing towards the negative direction. Okay. So that more or less brings us to a conclusion of today's lecture, but I'll give you a quick run up of what we are going to do in the next lecture. We're going to look at the special case of uniformly accelerated one-dimensional motion or motion along a straight line with uniform acceleration. So if our acceleration A is uniform, which basically means it's constant with respect to time. So what that means is that dv by dt, which is A, is constant. So that means v must be a linear function of time. And ts by dt is linear. That means s must be a quadratic function of time.
Do we have to note this down?
Yeah, we'll be looking at this in the next lecture, so you need not note this down. Okay, so this is s will be quadratic with respect to time. So we'll actually derive these equations using calculus. Okay. So we are going to look at the derivation by integration. That is dv by dt is equal to a, means that we can integrate this way. ts by dt is equal to u plus at. So that means now we can integrate this. And these integrations will give us these results. Okay. So this is something that we are going to look at in the next lecture. And then using these two equations, we have the third equation that v square is equal to u square plus 2as. So these three equations of and their applications, including the situation of motion, vertical motion under gravity. Like if we throw an object straight up, it goes up and comes down, or if we drop an object from a certain height, it comes down in a straight line, but in accelerated motion because of gravity. So that will also be an application that we will see in the next lecture. Okay, so that's coming up. Okay, so you can get started with a few applications of the concepts that we've learned today. That is the calculus type of definitions. Okay, using differentiation and all. There is an entire exercise of that in your calculus chapter of the module only, na? The exercise 4, the kinematics type of applications. So you can get started with those questions. I will give you a few selected questions. And also one more thing I wanted to tell you is that in exercise 2 of calculus, there are few tricky integrations towards the end. I don't know if you have completed that exercise or completed attempting that at least. So from about question 22 onwards till about the last question, which I think is 30 or something, there are quite a few tricky applications of integration by substitution. So please do a revision of the concepts that we have discussed in integration by substitution, like the simple substitution where a linear term is substituted, then the complicated one where you have a composite function f of gx into g prime x. So how we substitute in that. So we had done that in the lecture previous to your major test 2, but you might not have revised that before major test 2 because that was not part of this test syllabus. So please revise those integration by substitutions and do those last few questions of exercise 2 if you haven't already. Okay, 20th to about 30th question. So next time we will discuss some of those questions in class also. So be prepared if you have any doubts, because we really want to wind up calculus now. It's going to be all about kinematics the next few weeks. Okay, so that's it for today's session, people. Thanks for attending. Wish you all the best.
Thank you, sir.
Thank you, sir.
Bye, sir.
Bye, people.
Thank you, sir.
Okay, bye. Yeah, Ishan, I will share the recording and the notes, okay, as soon as possible. Today's session.
Bye, sir. Thank you.
Okay, bye, people. Bye.